Good morning, everybody. This is Mrs. Buchanan. I'm going to talk about limiting reactants in stoichiometry problems. So last week's lesson, you were not given the limiting reactant, or I gave you the limiting reactant, I should say. Um, you were always given one in excess, and you were given one you were told the amount of the one. Well, this week you're not going to do that. I'm going to give you both the amounts of both the amounts of the reactant, and you need to determine which one is the limiting reactant. So, what is a limiting reactant? Well, a limiting reactant is the reactant that is used up first. Limiting reactants determine the amount of product that is made and determine how much of the excess reactant is used. So we deal with limiting reactants all the time. We deal with limiting reactants in cooking and industry. It's the one reactant that is the most scarce or the one that is gone first that determines how much product you made. So I'm going to show you an example problem on how to determine the limiting reactant. So go through the same steps before. Balance the chemical equation. Convert grams of material to moles. Remember, the only thing that can go in a BCA table are moles. Step 3, determine the limiting reactant, and I'll explain that in the next slide. And then step 4, complete the BCA table once you've converted it to complete the BCA table once you determine the limiting reactant. Convert moles to grams because most of the problems are going to ask you for your final answer to be in grams. Remember, in order to go from moles to grams, you have to multiply by the molar mass. So your first example problem is this. So what I want you to write in your comp books, I want you to write aluminum reacts, so aluminum plus iodine. Remember, iodine is diatomic, so you have to write it as I2 to form aluminum iodide. So take a minute, pause the video, write out the reaction. So here's the reaction. It's Al plus I2 gives you AlI3. The coefficients are 2, 3, 2. So there's a few things to remember. Remember, 0 always goes in the before line on the product side because you haven't made anything yet. 0.5 moles of aluminum. So this problem was already converted to moles. So you have 0.5 moles of aluminum and you have 0.72 moles of iodine. So what you're going to do next is you are going to have to determine which one's your limiting reactant, and it's really a guess and check sort of thing. So the first thing you're going to do is I'm going to pick iodine as my limiting reactant because I want to show you an example of how it doesn't work out the first time. Maybe if you pick the wrong one, and it's okay, it's just some simple math you have to go back and do. So if you look over here, I pick aluminum to be the limiting reactant. So I'm going to take 0.5. So I'm going to use all 0.5 moles of aluminum up. And I'm going to divide it by 2. And I'm going to multiply it by 3 because those are the coefficients. So 0.5 divided by 2 multiplied by 3 will give you 0.75 moles. Now, this is how I think of the before line. The before line is like what's in my pantry. So I have 0.5 moles of aluminum and I have 0.72 moles of iodine. Not really, but you know what I'm talking about. So, but the problem is the change line tells you what you actually need to have for the reaction to progress. Well, I need 0.75 moles of iodine. I only have 0.72. So it doesn't work out that aluminum would be my limiting reactant because I have a negative 0.03 in my afterline and there's no negatives. It has to be 0 or excess over on the reactant side. It cannot be a negative number. So Al does not work as your limiting reactant. So I'm going to show you how it does work. So now I picked iodine as my limiting reactant. So I'm going to use all 0.72 moles of it. So 0.72 divide by 3 multiply by 2 will give you 0.48 moles of aluminum, which it works out because I have 0.50. I only need 0.48. So I have 0.02 in excess. I used up all 0.72 moles of iodine. Now, remember this. Once you pick your limiting reactant determines everything else. It determines how much product you made. So I made 0.48 moles of product, and it also determines how much of my excess I have left over. So once you determine that limiting reactant, it makes the whole problem work out the way it should. If that made sense, probably not. But anyway, 0.48 moles of aluminum iodine is then going to be converted to grams of aluminum iodide. So I'm going to take 0.48, multiply it by the molar mass, 407.68, and that gives me 196 grams of aluminum iodide. It also, the other part of the problem, also want to know how many moles of excess reactant will remain, while 0.02 moles of excess will remain after you do the calculations. So what I'm going to do next is we're going to move to a homework problem, and that would be in page, let's see, I believe it's page 14 in your homework packet, and I'm going to do an example with you on limiting reactants. Okay, so page 14, I believe it's page 14 in your packet. If not, look for this problem. If you have 34.5 grams of aluminum and it reacts with 23 grams of copper 2 chloride, how much copper is made? So this is a single replacement reaction. So what I want you to do right now is I want you to take a minute and I want you to write down aluminum plus copper 2 chloride, and I want you to predict the products and balance the equation. Pause the recording while you're doing this. Here's your reaction. So I have 2Al plus 3CuCl2 yields Cu plus 2AlCl3. Okay, so that's your balanced equation. That's the correct reaction. Remember, if you don't have the correct reaction and the correct balanced equation, this problem is not going to work out. Now, convert your grams of aluminum to moles. So you're going to take 34.5 grams and divide by 26.98. That will give you the moles of aluminum. And you're going to take 23 grams and divide by the molar mass of copper 2 chloride, and that will give you moles of copper 2 chloride. Take those amounts and fill in your BCA table in the before line. So you should have 1.28 moles of aluminum, and you should have 0.171 moles of copper 2 chloride. In the before line, you need to put 0, 0 as your product because you haven't made anything yet. Now is just your time to pick. Which one do you want to pick to be your limiting reactant? I mean, probably most of you will be able to see that what your best choice is by just looking at the ratios. For example, because you have such a small amount of copper 2 chloride, and when you divide it by 3 and multiply it by 2, it still is not going to be more than 1.28 moles. Some of you will have to sit down and do the math behind it, and that's fine. But don't always pick the one that has the least amount in moles because that's not always a great indicator. Just do the math. So copper 2 chloride is your limiting reactant. So I'm going to use all 0.171 moles of that. I'm going to divide by 3, multiply by 2. So that gives me a negative point, not negative. It means I consumed 0.114 moles of aluminum. Then I'm going to use my limiting reactant to determine how much product I've made. So 0.171 divide by 3, multiply by 3. That means I made 0.171 moles of copper. And then 0.171 divide by 3, multiply by 2. that means I made 0.114 moles of aluminum chloride. Okay, so here's your afterline. I have 1.17 moles in excess. That's what I have left over. I have 0 of copper 2 chloride because that's what was used up. That's my limiting reactant. So this is your LR is your copper 2 chloride. I'm trying to write this on with my Smart Notebook pen. 0.171 moles of copper are actually produced and 0.114 moles of aluminum chloride are produced. The problem says how much copper is made, so it's really asking you to convert it to grams. So take your moles and multiply it by the molar mass. So 0.171 moles of copper and multiply it by 63.55 grams, and you will end up with, in theory, 10.9 grams of copper. Now, you heard me say the word theory and kind of, exaggerate the way I said it, because that's what we're going to talk about next is theoretical and actual yield. A theoretical yield is something that in theory you're supposed to get. The actual yield is, or your actual amount is what you actually produce in lab. So I'm going to switch back over to my slides and talk about what percent yield is, because the second part of this lecture is talking about percent yield. So the percent yield is the ratio of the actual yield divided by the theoretical yield. It's like any percentage that you get, it's part over whole. Actual amount comes from the chemical reaction performing the reaction in a laboratory setting. The theoretical yield is the information or the amount that you get from the BCA table. So percent yield is the ratio of actual yield over theoretical yield. This value determines how efficient your reaction is. Theoretical yield is the maximum amount of product from a given amount of reactant. So in theory, we're supposed to get 100% yield all the time, but it doesn't always happen because many things can go on. The reaction doesn't go to completion. You could spill some of your reactants. Some of your products you could spill, depending. There's a million things that could go wrong. Some reactions, chemical reactions, are just not that efficient. So the actual is the measured amount of product obtained from the chemical reaction. This is the equation down here. Percent yield is equal to actual divided by theoretical times 100. So I'm going to actually ask you to go back to your packet and go to, I believe it's page 16, problem number 3. It says, what is the percent yield of NaCl if 7 grams of calcium chloride are used? If 7 grams are actually made. I think I might have wrote that wrong, but it's on page 16, number 3. No, are used up. I left out the word yet. I left out the word up, but are used up if 7 grams of NaCl are actually made. So what I want you to do is I want you to take, look at the problem, CaCl2 plus Na, and I want you to balance it. Come up with your coefficients. So here I came up with the coefficients. So I have CaCl2 plus 2Na yields Ca plus 2NaCl. Set up your BCA table, convert everything into moles. So you're going to take your 7 grams of calcium chloride, you're going to divide by the molar mass, which is 110.98, and you're going to come up with moles of calcium chloride. So that's 0.0631. And then you're going to have excess sodium, because you don't have in this problem, it didn't give you another amount for the reactant. So whatever it doesn't give you the amount for, that's the one in excess. So your products are 0, 0, because you haven't produced anything yet. So by default, calcium chloride is your limiting reactant. So go ahead, fill out the BCA table. So in theory, 0.126 moles of NaCl was formed. Before you can do percent yield, you got to convert it to grams. So take your moles of NaCl and multiply by the molar mass of NaCl. So 0.126 moles of NaCl, multiply it by 58.44 grams of NaCl. And in theory, you should get 7.36 grams of NaCl. Now calculate your percent yield. Percent yield is 7 grams. That's what you actually made in the lab. 7.36 grams is what you calculated from your BCA table. When you divide those and multiply by 100, you have a 95.1% yield. That's good. That means you're only lost less than 5% of it to an incomplete reaction, maybe spilling some reactants or products, something not going right in the reaction, but that's actually really good. The higher the yield, the better, the more efficient the chemical reaction. So what I'm going to have you work on for this week is some of the remaining homework problems in your packet, and there'll be another objective check at the end of the week. I'm trying to come up with different stuff since you're at home. Just bear with me. It would be nice that I see everybody during our Google Meets, just so I can touch base to see how everybody's doing and get feedback. The more feedback I get, the better this experience can be with you. It's not a perfect experience, but we're trying to make the best of it. So take care, and I will talk to you next week.